All right, you should have taken a short quiz on optimal resource extraction for a coal miner in one period with a finite stock of the resource. Here's what it looks like in graph form. The optimal choice of quantity for the owner of the small coal mine, who's a price taker. They can't affect prices. They have no monopoly power. So they would like to produce up to 50, but their reserves are 40, and so they have to produce, they can only produce 40. They can't produce 50 because there is not 50 units of coal under the ground. So here's their producer surplus. It's the area shaded in green everywhere underneath the price curve down to the marginal costs up to the reserves. Note that the production quantity is not determined by prices equal to marginal cost. Even though this coal producer is a price taker, this is a perfectly competitive market. And we've always been told that in a perfectly competitive market, prices equal marginal cost. But we see that that's not the case here. The firm would like to produce up to 50 units at a price of $110 per unit, but that's just that's not going to be possible with a reserve of 40. And so the price is the market price at 110, but the marginal costs are 90. So prices are greater than marginal costs. This difference is defined as the scarcity rent. It's the difference between the price and the marginal cost for the competitive resource owner. With only one period, the mine owner should either produce where price equal marginal cost or exhaust the reserves. So that's what we saw in the previous graph. The mine owner would like to produce up to the point where prices equal marginal cost, but the reserves don't allow that, so they produce less than produce less than to the point where prices equal marginal costs, and they've exhausted their reserves. So let's let Q wiggle, this Q tilde term, be the quantity at which P equals marginal costs, and R be the total reserves. If there's only one period, the mine owner will choose Q star, Q wiggle, I call that little squiggly line above the Q wiggle. Q star, the optimal amount is Q wiggle if Q wiggle is less than or equal to R. So Q wiggle is going to be up to the point where prices equal marginal cost, right? And if that point is less than the total stock of the resource, then that's how far, or that's how much the firm is going to produce. On the other hand, if Q wiggle is greater than R, and that's what we saw on the previous graph, then the resource owner is going to produce R. So for example, if Q wiggle is equal to 12, that's the point where marginal cost equal price, and R is 18, then they're going to produce 12. If Q wiggle is equal to 26 and R is 18, then they're going to produce 18. If Q wiggle is equal to 18 and R is equal to 18, then they would produce 18. So question, now suppose the mine owner has two periods in which to exhaust the resources. So far we've been dealing with one period, but now let's think about it as a dynamic problem. There's two periods. There's a lease that expires after 2 years. They don't actually own the land, they just own the lease to extract the coal, and they only have 2 years to do it. And each year the price is 110 and marginal cost is the same as it was before, 10 plus 2Q. The total reserves are 40. How much should the mine owner produce in each period? Assume that the mine owner has a discount rate of 10% and receives revenues and pays costs at the end of the year. Reminder, marginal cost equals price at 50, with 2 periods need a reserve of at least 100 to do that. So we would want to, if we had no resource constraint, we would like to produce 50 in each period, and so we would need a reserve of 100. But that's clearly not the case because our total reserves are 40. Now we have to break up this the stock of 40 units of coal into 2 periods of production. What's the best way to do that? Again, if reserves are sufficiently high, greater than 100, we would produce where marginal cost equals price in both periods. How much will the mine owner produce each period if total reserves are greater than 100? Answer, 50 units each period. If doing so does not exhaust the reserves, it is optimal for the mine owner to choose quantities so that marginal costs equal price in each period. However, if there are not enough reserves to set marginal costs equal to price in each period, will the mine owner use all the reserves? Of course they will. Why would they not? Otherwise, it's possible to produce another unit, and doing so will increase profits because marginal costs would be lower than price. So they should exhaust their total stock of resource over the 2 years. How are they going to decide how to do this? Well, a rational coal mine owner will maximize the present value of profits over the 2 periods. To maximize the present value of profits, they're going to allocate extraction so that the present value of a marginal increase in profits is the same across all time periods. In other words, it's impossible to do better being defined as increased profits, by moving a unit of the resource to a different time period. For any firm, the marginal increase in profits from producing an additional unit is marginal revenue minus marginal cost. So what is the marginal revenue for a price-taking firm? Let's solve the problem. Let Q1 and Q2 be the quantities produced in periods 1 and 2, and let P1 and P2 be the prices in periods 1 and 2. The present value of a marginal increase in profits is in period 1 is 1 over 1 plus R, where R is the discount rate, times P1 minus the marginal cost at Q1. And we can substitute in the marginal cost function here, so then we get that's equal to 1 over 1 plus R, the discount factor, times P1 minus 10 plus 2Q1. We can do the same thing for the second period, and that's what we see in the equation below. And so now we have the discount rate, or the discount factor, raised to the second power because we're in the second time period. Technically, we also have the discount factor raised to the first power in the first equation, but we leave that out because raising to the first power does nothing. And so now we have two equations, where one tells us the marginal profits discounted to the present value in period 1, and the other tells us the marginal profits discounted to the present value from period 2. Now, in order to solve this problem, we have to satisfy two conditions. First, the present value of marginal profits is the same across all periods. And so we're going to take our equations from the previous slide and set them equal to each other. And then second, all reserves must be exhausted by the end time period. And so these two equations have two unknowns in them, Q1 and Q2, and we have two equations, so we can solve for Q1 and Q2. How should the coal owner allocate production over time? Should they do it all in year 1? So we're going to solve this problem graphically first, and then we'll do it analytically. So if the resource owner allocates production all in year 1, their producer surplus is going to be, or their profits in this case, present value of profits is the green polygon. There's zero profits in year 2 because there's zero production in year 2. We've used up the entire stock of the resource in year 2, and profits are $2,182. What if we move a small amount of production from year 1 to year 2? This will increase the present value of profit. So let's see what our total profits are in this case. So now we have a small amount of production moved from year 1 to year 2. Our profits on that bit of production in year 1, or the difference between the price and the marginal cost, that area is fairly small in year 1, and then if we substitute that for production in year 2, you can see the area lost in year 1, the area that's not produced anymore in year 1, now that's being replaced by a larger green polygon in year 2, so profits are going to increase slightly. So profits went up a bit by reallocating some production from year 1 to year 2. Can we do even better? We have 2,461 and for profits this period, or with this allocation of production. Now let's look at a slightly different allocation of production. All right, now we're allocating a little more from year 1 to year 2, and our profits went up even further. We're at 2,653. So what's going to get us to the optimal amount of production? Should the firm set quantities in each year equal? Equalize the scarcity rent in each period. So now we've gotten up even further from the previous slide. Our profits are now 2,777 by producing 20 in each period. But this doesn't account for discounting, right? So we value the production in year 2 slightly less than we value the production in year 1 due to the discount factor. And so we can improve upon this just slightly by increasing our production a tiny bit in year 1 relative to year 2. So let's look at that. So we can earn slightly higher profits by equalizing the present value of scarcity rent in each year, slightly more produced in year 1 because of discounting. So now we've gone up a little bit in profits by producing, instead of equal amounts in year 1 and year 2, we produce slightly more in year 1 than we do in year 2. So we can see this in another way. This graph shows the quantity in year 1 produced in year 1 in the x-axis, and the present value of total profits on the y-axis. And if we, in 20 is going to be cutting the total reserves in half and producing half in year 1 and half in year 2, you can see that the peak of this curve, the peak of the profits, is slightly to the right of 20, and that's what we saw in the previous graphs. So we're almost at the peak of profits if we cut our production in half between year 1 and year 2, but we can do slightly better by producing a little bit more in year 1 than year 2, and that's because of discounting. With no discounting, this would shift to, we would maximize our profits by producing 20 in year 1 and year 2. So what does this imply for the market price? Okay, so we suppose that instead of a single coal mine owner, we have numerous small identical mine owners. All of them are price takers. Each firm solves the above problem, so we already know the optimal extraction for each firm satisfies satisfies this present value of profits equation. We can take this and multiply by 1 plus r squared, so that's going to get rid of the discount rate on the right-hand side, and it's going to leave us with the equation, the second equation on this slide, 1 plus r times P1 minus marginal cost of Q1 equals P2 minus the marginal cost of Q2. We can interpret this condition as saying something about the path of prices in the industry. How are prices going to increase? This leads us to Hotelling's rule. In a competitive resource extraction industry, the scarcity rent, the price less marginal cost, grows at the discount rate. Or we can think of this as, in a competitive resource extraction industry, the present value of the scarcity rent is the same for all periods. So the difference between these two sentences is the scarcity rent grows at the discount rate, or the present value of the scarcity rent is the same for all periods. They say the same thing, but one is about the present value. So let's get back to prices. Consider the case where marginal costs are 0. So if we go back to 2 slides ago, where we had the equations on the slides, and we set marginal costs in both periods equal to 0, we get the following equation: 1 plus r times P1 equals P2. So this should give us some intuition for what's happening in the prices. Prices are rising at the interest rate. The price in period 2 is equal to the price in period 1 times the interest rate, or the discount rate. This should be unsurprising. And here's the intuition for this. Suppose the price is $10 in period 1 and the discount rate is 10%. If the price were 10 in period 2, who produces in period 2? The answer is no one. Producing in period 1 and investing the profits yields 10 times the discount rate, or the interest rate of 1.1, which equals 11 in period 2. So you can do better by extracting the entire resource today, selling it, and investing the profits. This is true for any price less than $11, and therefore the price must rise in period 2 in order to induce production in that time period. If the price were 12 in period 2, who would produce in period 1? So this is the opposite case. The answer is no one. Producing in period 2 yields 1 over 1.1 times 12, which is greater than 10 in period 1. So the only stable price path is the one in which prices rise at the interest rate. The general case with positive marginal costs, prices must be such that price less marginal cost rises at the rate R. In other words, the scarcity rent rises at the interest rate. If this were not the case, then you would see resource owners leaving the resource in the ground, either in periods 1 or period 2. This also can tell us about how the quantity extracted changes over time. Right, so if the price increases over time, the extracted quantity must fall over time. We have to assume that the demand for the resource is constant over time. The costs and the discount rate are also assumed to be constant. In other words, the production costs are constant. If the price of the resource is increasing, what must happen to the extracted quantity? Well, it must be declining over time. Why? The supply must equal demand, and at higher prices, a smaller quantity of the resource is demanded. This is just the law of demand. So let's summarize our results. The results for a competitive non-renewable resource extraction industry assuming no change in demand, costs, or the discount rate over time. 1. Scarcity rents rise at the discount rate. We can say that another way. The present value of scarcity rents is constant. 3. Quantity extracted per period falls over time. Number 4, the resource prices rise over time at a rate less than or equal to the discount rate. So this is what we saw in the previous slides. The prices are rising, particularly if marginal costs are 0, the prices are going to rise at the discount rate. But if marginal costs are not equal to 0, then scarcity rent is going to rise at the discount rate. And then, of course, by the law of demand, the quantity extracted per period falls over time. So for the reading for this, I'm posting parts of the Hoteling Under Pressure article by Soren Anderson, Ryan Kellogg, and Stephen Salant. Specifically, I want you to read sections 1 and 2 in the conclusion.